Hello and welcome. Settle in, because today we are going on a real expedition. This isn't just a surface-level overview. We're embarking on a truly comprehensive, incredibly detailed deep dive into the very heart of modern telecommunications. Think of this as a masterclass. We're going to journey from the massive, industry-shaping principles that are remaking a multi-trillion-dollar global business all the way down to the nitty-gritty, line-by-line mechanics of how this revolution is actually being implemented. We will be meticulously, and I mean meticulously, dissecting the future of what's called the Radio Access Network, or the RAN. You know, that's the crucial and often invisible part of the mobile network that connects your phone to, well, everything else. Specifically, we're going to explore how a profoundly important open-source project called Nephio is said to completely change the game for network automation. And it does this by bringing to life a critical standard from the O-RAN Alliance, the O2 interface. This topic, I promise you, sits right at the intersection of 5G, hyperscale cloud computing, and massive autonomous automation. Understanding it with the depth we're about to provide isn't just a nice-to-have. It is absolutely the key to seeing where the entire telecommunications and cloud industry is headed for the next decade and beyond. So please, get comfortable. We're going to take our time. We're going to go deep.
Now, to navigate this incredibly rich and, let's be honest, complex landscape, we've structured this entire explainer as a six-part journey. Each part builds directly and logically on the one before it, and we're going to dedicate significant time to each one to make sure everything is crystal clear. First, we're going to set the grand stage by looking at the evolution of the RAN itself. We have to ask, why is this massive revolution even happening? What were the technological and economic forces that made this change not just possible but inevitable? Second, we'll carefully deconstruct the O-RAN architecture. This is where we'll build our vocabulary, defining the key building blocks like the SMO, the O-Cloud, and the interfaces that connect them. Third, we will formally introduce our main character, Nephio, and we'll spend some real time on its core philosophy, these powerful ideas of intent-driven and declarative automation. Fourth, and I want you to pay close attention here, because this is the technical heart of our entire discussion, we will trace, step by painstaking step, exactly how Nephio realizes the O-RAN O2 IMS interface to build cloud infrastructure from nothing. Fifth, we'll dive into a really fascinating architectural debate. Is the system two-tier or three-tier, and why does that distinction matter so much? And finally, in part 6, we'll zoom back out to appreciate the incredible scope of Nephio's vision, seeing how these same core principles apply to the entire network. This is our roadmap. Let's begin our expedition.
All right, part 1. You know, to truly, deeply grasp the importance of a tool like Nephio, or a standard like the O2 interface, we absolutely have to start at the very beginning. It's just not enough to look at the new thing, to look at the code or the diagrams in isolation. We have to understand the history, the context, the fundamental, industry-wide tectonic shift that's been building for more than a decade. This isn't just about a new piece of software. This is about a complete and total philosophical reimagining of how cellular networks, which are truly one of the most complex engineering achievements of humankind, are designed, built, and operated. The intricate how of a project like Nephio only really shines. It only becomes truly illuminated when we first take the time to deeply and thoroughly understand the powerful why that's driving this entire global transformation. The shift from these old proprietary monolithic boxes to a disaggregated, open, cloud-native software world. This slide right here perfectly captures the earthquake that has defined the last 30 years of telecom. For decades, the entire world of the radio access network was defined by the model you see on the left, the monolithic RAN. Let's really spend a moment to paint a picture of this world. Think of it as a fortress, a hermetically sealed black box. A single powerful vendor, and there were really only a handful to choose from, would provide this massive, proprietary piece of hardware. And inside that box, you had all their custom-designed silicon chips and all their highly optimized secret sauce software. All of it tightly integrated and engineered to work only with itself. Now, for a network operator, this did have some advantages, right? It was battle-tested, it was reliable. If something went wrong, you had one throat to choke, a single phone number to call for support. But the drawbacks were monumental, and they shaped the economics of the entire industry. It created this ironclad vendor lock-in. Once you chose a vendor, you were stuck. You were tied to their hardware, their software, their pricing schedule, and their innovation cycle for years, sometimes for decades. Innovation was painfully slow because it was gated by that one vendor's multi-year development roadmap, and the costs were just incredibly high because there was no real competitive pressure to bring them down. Now let's look to the right. The new way, the disaggregated RAN, represents a radical philosophical break from all of that. Instead of one giant fortress, the network is carefully deconstructed into smaller, distinct components. And the critical innovation, the absolute key that unlocks this whole new world, is the creation of open, standardized interfaces connecting them. This changes literally everything. For the first time ever, a network operator can now pick and choose the absolute best-in-class components from a vibrant, buzzing ecosystem of different vendors. They can buy the best radio unit from company A, the best real-time software from company B, and the best management software from a startup, company C. And they can be confident that all these parts will interoperate because they all speak the same language defined by those open standards. This, of course, unleashes the powerful forces of market competition, which relentlessly drives down costs. But maybe even more importantly, it fosters this Cambrian explosion of innovation at every single layer of the stack. Why? Because a small, smart startup can now focus all its energy on perfecting just one component, instead of trying to build the whole monolithic fortress. Fundamentally, this revolution transforms the RAN from a rigid, hardware-centric problem into a flexible, dynamic software-defined ecosystem. And this is the bedrock for everything else we're about to discuss today.
So let's get a bit more specific. What does this word disaggregation actually mean in practice when we're talking about a modern 5G base station, or a GNOB, as it's called in the standards? It means taking that big monolithic black box and carefully splitting it apart along logical functional lines. As the source material explains, it's separated into three primary units. First up, you have the RU, the radio unit. This is the part that actually lives at the top of the cell tower. You know, the component with the antennas and the power amplifiers that physically sends and receives the radio waves that communicate with your phone. It's living out there in the elements. Then you've got the DU, or distributed unit. This component usually sits at the base of the tower or nearby, and it's responsible for the extremely time-sensitive, real-time parts of the radio protocol stack. We're talking about things that have to be processed in mere microseconds, or the signal just doesn't work. And finally, you have the CU, the centralized unit. This can be located much further away, maybe in a local data center or an edge cloud, and it manages the less time-critical, higher-level protocol functions, often for many different cell sites at once. Now, the absolute, non-negotiable, most important key to making this entire model work is the standardization of the interfaces between these units. I can't stress this enough. Without a standard way for a CU from vendor X to talk to a DU from vendor Y, which in turn needs to talk to an RU from vendor Z, you just have an expensive pile of incompatible parts. It would be a total failure. But with standards bodies like the O-RAN Alliance defining these open interfaces, like the crucial open front-hole interface between the DU and the RU, we finally enable a true, vibrant, multi-vendor ecosystem to flourish. This functional deconstruction is the first, essential, and foundational step towards building an open RAN.
So once you've successfully disaggregated the functions of the base station into these logical software blocks, the next evolutionary step becomes immediately obvious: virtualization. You have to ask yourself, if the CU and the DU are now primarily defined by their software functions and not their physical form factor, why on earth do they need to run on specialized, eye-wateringly expensive proprietary hardware built by a single vendor? And the simple, revolutionary answer is, they don't. Virtualization is the critical process of decoupling that network function software from the specific underlying hardware it runs on. And this is a monumental change in the economics and operations of a telecom company. It means you can now take the brains of your cell network, that CU and DU software, and run them as virtual machines, or even better, as containers on generic, commercial off-the-shelf, or COT servers. We're talking about standard data center hardware, the same kind of servers from companies like Dell, HP, or Supermicro that run websites and banking systems, powered by standard Intel or AMD processors. This dramatically lowers capital expenditure, or CapEx, because this commodity hardware is just far, far cheaper than specialized telecom gear. But even more importantly, it fundamentally transforms a hardware lifecycle management problem, which is slow and expensive, into a software lifecycle management problem, which is fast and automatable. And that change is what flings open the door to the final and most powerful evolutionary step in this journey.
In that final step, the ultimate destination of this whole evolution is to become cloud native. Now, this is one of the most important and honestly most often misunderstood terms in technology today. It is so much more than just taking some old software and running it in the cloud. That's just cloud-hosted. Cloud-native is a complete paradigm shift in how you architect, build, deploy, and manage software applications from the ground up. Instead of having these large, monolithic applications where a single bug in one part can bring down the entire system, functions are broken down into a suite of small, independent, and loosely coupled microservices. Then, each of those tiny microservices gets packaged up along with all of its dependencies into a lightweight, portable, and isolated unit called a container. You've probably heard of Docker, which is the most famous technology here. And this entire fleet of thousands or even millions of containers is then managed, scheduled, and orchestrated by a dynamic, resilient, and automated platform. And the undisputed king, the operating system of the cloud, is Kubernetes. When a network function truly becomes cloud-native, it inherits the superpowers of the cloud. It becomes incredibly resilient, because if one microservice fails, the orchestrator, Kubernetes, can restart it instantly without affecting any of the others. It becomes incredibly scalable, because you can spin up or spin down hundreds of copies of a microservice to meet real-time demand, automatically. And it becomes far easier and safer to update, because you can deploy new versions of just one single microservice without having to take the entire network down for maintenance. This philosophy of dynamic, declarative, automated software management is absolutely essential for delivering on the promise of ORAN. And as our source material states, platforms like Nephio, which were born from this cloud-native world, are a perfect fit for managing this new reality.
All right, we've done the groundwork. We have now established the deep historical and technological why behind all this change. The entire industry is making this painful but absolutely necessary transition towards a disaggregated, virtualized, and cloud-native model to unleash competition, drive down costs, and accelerate the pace of innovation. So now that we have that foundational understanding locked in, let's start mapping out the what. We're going to deconstruct the new world as it's being defined by the ORAN Alliance. In this section, we'll take our time to introduce the key architectural components, the new building blocks of the network, and, most importantly, the critical interfaces that connect them all together. This will give us the precise vocabulary and the mental model we need to understand exactly where a powerful automation platform like Nephio fits into this grand design.
This slide gives us a fantastic high-level map of the logical ORAN architecture. Let's think of it as a layered stack, a layer cake, if you will, and we're going to walk through it from the top down. At the very top, in Layer 1, you have the SMO. That stands for Service Management and Orchestration. You can think of this as the master brain of the whole operation. It's the CEO, the central nervous system of the entire radio access network. This is where the high-level business and operational goals are set. Now, sitting just below the SMO, acting as the critical communication channel to the next layer down, is the O2 interface. This is the standardized set of commands and protocols that connects the brain to the underlying infrastructure. We're going to be focusing a lot on this interface. The O2 interface talks to the O Cloud, which is our standardized telco-grade cloud computing platform where all the software actually runs. You can think of this as the factory floor. And finally, at the bottom layer, running on the O Cloud are the actual network functions we spent so much time defining in the last section, those containerized CUs and DUs that are doing the real work of processing the radio signals. Now let's break down each of these layers in much, much greater detail.
So let's start at the absolute top of that stack with the SMO. This is the command and control center for the entire Open RAN. As the source material points out, the SMO is responsible for the complete lifecycle management of the RAN, and that means everything from the initial deployment and turn-up to ongoing optimization and performance management, and eventually to decommissioning. Now, internally, the SMO isn't one single piece of software. It's really a collection of logical functions all working together. For our discussion today, the two most relevant functions are NFO, which is Network Function Orchestration, and OFO-COM, which stands for Function and Orchestration Management. Let's be very clear about their distinct roles. Think of NFO as being responsible for the lifecycle of the network services themselves. It's the part that says things like, I need to deploy a brand new 5G slice for a big enterprise customer, or we need more capacity in downtown. OFO-COM, on the other hand, is the SMO specialist for the underlying cloud resources. It's the SMO's infrastructure agent. So when the NFO decides it needs a new 5G slice, it's the OFO-COM function that is tasked with the job of making sure the necessary cloud infrastructure, the virtual machines and Kubernetes clusters, actually exist to host that slice. It is the OFO-COM that will initiate the requests over that O2 interface that we'll be dissecting. So for our purposes, OFO-COM is the part of the SMO that is the direct client
the customer, for the automation we're about to witness.
Now, where do these virtualized CU and DU network functions actually live? They live on the O cloud. And it's critically important to understand that the O cloud is not just any cloud. It's not simply a generic AWS or Google Cloud environment that's been repurposed for telecom. It is a cloud computing platform whose architecture, interfaces, and expected behaviors are being standardized by the O-RAN Alliance. This is absolutely vital for achieving that multi-vendor promise we talked about. The O-Cloud itself consists of two main parts: the physical hardware layer, that's the COTS servers, the storage arrays, and the high-speed networking fabric, and a cloud software stack built on top of all that hardware. This software stack almost always includes a platform like OpenStack for managing virtual machines, and layered on top of that, a platform like Kubernetes to manage the containerized network functions. By standardizing the O-Cloud's APIs and its expected behaviors, the Alliance ensures that an SMO from one vendor can successfully manage an O-Cloud from another vendor, which in turn can host network functions from a third, fourth, or even fifth vendor. This is interoperability in action, and it's what prevents the reemergence of vendor lock-in at this new cloud layer.
And this brings us to the linchpin of the entire system, the central topic of our explainer today, the O2 interface. The O2 interface is the standardized API-driven communication link that connects the SMO, our network brain, to the O-Cloud, our standardized computing platform. This interface is the contract. It's the legally binding agreement, if you will, between the manager and the managed resources. It's what allows the logical separation between the SMO's high-level goals and the O-Cloud's low-level execution. The source material emphasizes that through this single standard interface, the SMO can perform two fundamentally different but intimately related jobs. First, it can provision and manage the cloud infrastructure itself, and second, it can deploy and manage the network function workloads on top of that infrastructure. This dual responsibility is so important and so distinct that the O2 interface itself is formally broken down into two separate logical services, which we absolutely must explore in detail.
This distinction between IMS and DMS is absolutely fundamental, so let's spend some significant time right here to make sure it's crystal clear. On the left, we have O2 IMS, the Infrastructure Management Service. This is all about preparing the ground. It's about the foundational layer. Let's use that factory analogy. A request sent over the O2 IMS interface is like the order to the construction company. It says, I need a 50,000 square foot factory building at this location with this much power, this many loading docks, and an HVAC system capable of maintaining this temperature. In technical terms, as our sources state, this means things like provisioning a bare metal server from a pool of available hardware using a tool like Metal 3. Or, more commonly, it means creating a brand new, fully configured managed Kubernetes cluster, like an EKS cluster on AWS or a GKE cluster on Google Cloud. The IMS is responsible for creating the environment where work can happen. It builds the stage. Then, on the right, we have O2 DMS, the Deployment Management Service. This is about what you do inside the factory that you just built. It's about installing the assembly lines, the robotic arms, the conveyor belts. The DMS interface is used to deploy, manage, and configure the actual workloads, those containerized CU and DU network functions, onto the pristine infrastructure that the IMS just created. So, to be perfectly clear, IMS builds the Kubernetes cluster, and then DMS deploys the CU application pods onto that cluster. They are two sides of the same coin, and they manage the same physical resources, but they operate at totally different levels of abstraction. IMS manages the platform, DMS manages the applications that run on the platform. Understanding this clean separation of concerns is the absolute key to understanding how a tool like Nephio can provide such an elegant and comprehensive solution.
We have methodically, carefully set the stage. We've defined the new, disaggregated, cloud-native reality of the modern RAN. We've deconstructed the complex O-RAN architecture that governs this new reality. And now, at last, it is time to introduce the protagonist of our deep dive, Nephio. Nephio is a Linux Foundation open source project. It was originally conceived and open sourced by Google and is now supported by a wide and growing consortium of industry players, including major network operators and vendors. It was designed from the ground up, from first principles, to specifically tackle the immense, mind-boggling complexity of configuring, deploying, and managing these disaggregated cloud-native networks at a massive scale.
It's not just another automation script or a simple workflow tool. It represents a fundamental shift in the philosophy of network management. Let's spend some time exploring what makes its approach so different and so powerful.
This quote, right from our source material, perfectly and concisely captures Nephio's core identity. It uses three very powerful, very specific, and deeply meaningful terms: intent-driven, declarative, and cloud-native. Now, we've already spent a good bit of time understanding the cloud-native paradigm, but these other two concepts, intent-driven and declarative, are the twin pillars that support Nephio's entire philosophy. They represent a deliberate, conscious move away from the old world of complex, brittle, imperative scripting towards a far more robust, intelligent, resilient, and scalable model for automation. To truly understand what Nephio is and why it matters so much, we have to now break down exactly what each of these powerful terms means in a practical sense.
First, let's really tackle this idea of being intent-driven. This represents a profound shift in how we as humans interact with complex systems. In the old world of imperative automation, you had to provide the system with a detailed, step-by-step recipe of commands to get what you wanted. You were responsible for specifying the how. An intent-driven system, by powerful contrast, only asks you to specify the what. You simply declare your desired final outcome, your ultimate goal, and you delegate the entire responsibility for achieving that goal to the automation system itself. Let's use that pizza analogy because it's perfect. The old imperative way of getting a pizza would be like providing a script that says, Step 1, drive to the grocery store. Step 2, buy flour, yeast, tomatoes, and cheese. Step 3, drive home. Step 4, knead the dough for exactly 10 minutes. Step 5, preheat the oven to 450 degrees, and on and on. It's incredibly complex, and it's brittle. If any single step fails, if the store is out of cheese, or if there's a traffic jam, the entire process breaks down. The new intent-driven way is simply stating, I want a large pepperoni pizza delivered to my address in 30 minutes. You declare your intent, the what, and the system, in this case, the pizza shop's entire logistics, cooking, and delivery operation, is responsible for figuring out the complex how. Nephio applies this same powerful principle of abstraction to the infinitely more complex world of network orchestration.
Now, the concept of declarative is the practical mechanism that makes the intent-driven philosophy a reality. If intent is the what, then declaration is how we write it down. Instead of writing a script full of actions or verbs like create this, configure that, start this, you create a data file. Typically, it's in a human-readable format like YAML, and it simply declares what the final state of the world should look like. It's a noun-based description of your desired end state. The perfect analogy for this, and we have to use it, is the thermostat in your home. You don't give your HVAC system an imperative script like turn on the furnace for 10 minutes, then turn it off, then check the temperature, then turn on the air conditioner for 5 minutes. That would be insane and impossibly brittle. Instead, you use a simple declarative interface. You set the thermostat to 72 degrees Fahrenheit. You have declared the desired state, and then the system takes over. It enters what's called a reconciliation loop. It continuously compares the actual temperature in the room, the current state of reality, to your declared temperature, the desired state. And it automatically takes the correct action, turning on the heat or the AC, to close that gap. It never stops this process. It's always watching, always reconciling. This continuous reconciliation is the very essence of the declarative model, and it's what makes systems built on this principle, like Kubernetes and like Nephio, so incredibly robust and self-healing.
This side-by-side comparison makes the fundamental difference starkly, brilliantly clear. The imperative approach, on the left, is typified by a fragile script of commands. It's a one-way fire-and-forget street. You run the script, you cross your fingers, and you hope for the best. The script itself has no knowledge of the desired end state. It only knows the very next step in its own sequence. If a step fails halfway through, the system is left in some inconsistent, unknown, broken state. And even worse, if a human operator manually goes in and changes something after the script has already run successfully, the system is now in an unmanaged state known as configuration drift, and the original script has absolutely no idea that reality has changed. The declarative model, on the right, is a completely different universe. The manifest, that YAML file describing the goal, becomes the single source of truth for how the world is supposed to look. The system's job is to be a relentless, tireless reconciler. It is always watching, always comparing reality to the declaration. If a server that is part of your declared state crashes, the reconciler sees the discrepancy and automatically provisions a new one to replace it. If a configuration parameter is manually changed by an operator and it drifts away from the declared state, the reconciler detects it and automatically changes it back. This makes the system incredibly robust, predictable, and autonomous. It's a fundamental paradigm shift from one-time execution to continuous closed-loop management. So how does Nephio actually apply these powerful principles of intent-driven declarative automation? Well, as our source material lays out, its architecture is deliberately designed to address the full spectrum of network automation across three critical management verticals. First, there is infrastructure management. This is all about provisioning the foundational layer of the cloud, the bare metal servers, the virtual machines, the Kubernetes clusters. This maps directly and perfectly to that O2 IMS interface we spent time defining earlier. Second, there is workload management. This is about deploying, connecting, and managing the actual network functions, our CUs and DUs, on top of the infrastructure that was just created. This clearly aligns with the role of the O2 DMS interface. And third, there is lifecycle management. This goes way beyond the initial deployment to handle all the ongoing configuration and updates, what's often called Day 0, Day 1, and Day N configuration. This aligns with another important OREN interface, the O1 interface. This holistic, three-pronged approach is what makes Nephio a true end-to-end orchestration platform, not just a point solution for one small part of the problem.
Okay, this is it. This is the centerpiece of our explainer. We have now covered all of the necessary theory. The historical evolution of the RAN, the complex ORAN architecture that governs it, and the core philosophical principles of Nephio. Now, we are going to get intensely practical. We are going to meticulously trace the entire automation workflow, following a single request, from the moment it's born all the way to its fulfillment, to see exactly how a high-level intent from the SMO is ingested, processed, and transformed by Nephio into a fully provisioned, live, and running Kubernetes cluster. In doing this, we'll see precisely how Nephio realizes the ORAN O2MS standard. This is the section where all the abstract pieces we've assembled finally come together into a beautiful working machine. This slide is our master plan. It's our assembly line diagram for this entire section. It lays out the 5 key stages of the Nephio automation workflow. Let's think of this as following an order through a factory. It all begins at the top with the SMO's FOCOM function specifying a high-level intent. That's the customer placing an order. That intent then triggers a Nephio controller, which goes to the warehouse and fetches a generic template, which we call a base package. Then, in step 3, that generic package is sent down an assembly line where it is curated and customized by a series of specialized robotic arms, which we call specializers. In step 4, the final, fully formed, ready-to-deploy package is pushed to a Git repository, which acts as our system's single source of truth and our quality control checkpoint. And finally, in step 5, a reconciliation engine out in the field picks up that configuration from Git and makes it a reality, creating the live cluster. We are now going to walk through each of these 5 steps in immense detail.
Everything begins with step 1, the intent. As the source material describes, the SMO's FOCOM function has determined that it needs a new Kubernetes cluster to host a future network function. And it doesn't provide 1,000-line scripts or a complex sequence of API calls. It provides a simple, high-level, human-readable declaration of its needs, expressed purely as data. Look at this example. It wants a managed Kubernetes cluster from Amazon Web Services, known as EKS. It specifies the geographical location, US-East 1. This simple string has huge implications for things like data sovereignty and latency to end users. It requests a large node profile, which is a powerful abstraction. It doesn't need to know the specific AWS instance types. It just knows it needs a large amount of resources, which might map to specific CPU and memory configurations defined elsewhere. And it wants a very specific Kubernetes version, 1.28, which might be required for compatibility with certain network functions or because it contains critical security patches. This is the simple beauty of the intent-driven model. All of the immense operational complexity of actually creating that cluster is completely abstracted away from the user. The user simply states what they want in a clear, concise data structure. And this intent, this custom resource, becomes the trigger for the entire downstream automation chain.
Once that intent is created and received by the system, Nephio's machinery kicks into gear. Step 2 involves what the source calls base packages. These are managed using a tool from the Kubernetes ecosystem called KPT, which stands for Kubernetes Package Tool. The absolute best way to think of a base package is as a master blueprint or a certified template. For our EKS cluster example, a central platform engineering team would have pre-created a base package containing all the standard generic YAML files needed to define any EKS cluster according to their organization's best practices. This package would include definitions for networking, for security policies, for logging, for monitoring, and so on. It is a validated, secure, and reusable starting point. And, crucially, as this slide says, it has placeholders for things like the region, the node size, or the cluster name, but no specific values are filled in yet. Using these base packages is absolutely vital for governance and consistency. It ensures that every single deployment, out of potentially thousands, starts from a known good, compliant configuration. It prevents the creation of snowflake clusters, which are all slightly different and impossible to manage, and it ensures uniformity across the entire global network.
Step 3 is where the real intelligence of the system, the real magic, comes to life. This is the process Nephio calls curation. A core Nephio controller is constantly watching for new intents to appear. It sees the high-level EKS cluster intent that we created in Step 1. Based on the type of that intent, it knows which blueprint to use, so it programmatically fetches the correct EKS base package from our repository in Step 2. Now it has a generic blueprint and a specific request, and its job is to combine them, to transform the generic into the specific. It does this, as the source explains, with the help of a whole fleet of other controllers called specializers. You can think of these specializers as small, expert, single-purpose robots on our automation assembly line. One specializer might be an expert on AWS regions. It reads the US-East1 value from the intent, and it knows to inject that value into the dozen different places it needs to go within the various YAML files. Another specializer might be a capacity expert. It reads the large profile request from the intent, looks up in a central database that large for this region means M5.2x large instance types with 8 CPUs and 32 GB of RAM, and it injects those specific values. Another specializer still might be a security expert that injects the correct network security group IDs based on the cluster's location and purpose. The package runs through this pipeline of specializers, each one adding its layer of specific detail, and to the generic blueprint has been fully and automatically curated into a complete configuration that perfectly and precisely matches the user's original high-level intent.
This brings us to the final 2 steps of our workflow, which together form a powerful and modern automation pattern known as the GitOps reconciliation loop. In Step 4, that final, fully curated package of YAML files, our completed blueprint, is not applied directly to any API. Instead, it is programmatically committed and pushed to a dedicated Git repository. This Git repository now becomes the immutable single source of truth. The complete, desired state of our infrastructure is now explicitly declared, it's version controlled, and it's stored in Git. This provides a full, undeniable audit trail. We can use standard Git tools to see exactly who requested what, when it was approved, and precisely what configuration changes were made. Then comes Step 5, the execution. A reconciliation engine, which is a piece of software like Argo CD or Flux, is running in the target environment in our O Cloud, and it is configured to constantly watch this specific Git repo. As soon as it sees the new commit containing our EKS cluster package appear in Step 4, it swings into action. It pulls down that configuration and compares it to the state of reality in its cloud account. It sees that the declared EKS cluster does not exist, so it begins making the necessary API calls to AWS to create the cluster, configure its networking, and provision its nodes. This is that continuous reconciliation loop we talked about with the thermostat. And from this point forward, that engine's only job, 24 hours a day, 7 days a week, is to ensure the live, running cluster always and perfectly matches the configuration that's declared in that Git repository.
Now, for any of the system architects and standards experts in our audience, the deeply detailed workflow we just described might raise a very interesting and subtle question. The official ORAN standard documentation appears to describe a very simple 2-part or 2-tier architecture. However, the practical Nephio implementation we just walked through, with its separate management cluster and its GitOps loop, appears to introduce an extra logical layer, making it look like a 3-tier architecture.
This section, which is based on a fantastic and insightful Q&A from our source material, dives headfirst into this apparent discrepancy. We're going to frame this as an expert dialogue, addressing a key point of potential confusion and showing how a theoretical standard can be reconciled with a practical, powerful, real-world implementation without any contradiction at all.
So here it is, the central question. A question that, as our source document notes, was raised directly by a contributor from the ORAN working group itself, so this is a real-world concern. The official standard specifies a two-tier architecture for the interaction between the SMO and the OCloud over that O2 interface. But the Nephio flow we just meticulously walked through, with its central management cluster of controllers that curates packages and pushes them to Git, looks for all the world like a three-tier architecture. So, are they incompatible? Does this powerful Nephio implementation actually break the ORAN standard? This is a fantastic and really important question because it gets right to the heart of how high-level standards and real-world implementation tools must interact and coexist in a healthy ecosystem. Let's break down the two views.
On the left, we have the simplified, logical view taken directly from the ORAN standard. It shows a very clean, two-tier model. You have the SMO, our top-level brain, and it communicates directly with the O2 IMS interface, which is logically considered a service that is exposed by the OCloud itself. It's a direct, peer-to-peer conversation over a standardized API. The SMO says, "Give me a cluster," and the OCloud responds. It's simple and clean. On the right, we have the Nephio implementation reality that we just detailed. And here, the SMO doesn't seem to talk directly to the final workload cluster at all. It talks to an intermediary layer, which the source material calls the Nephio management cluster. This is the logical place where all those intent controllers, the specializers, and the capped package management functions actually live. This management cluster then operates on the final OCloud workload cluster, but not through a direct API call. It does it indirectly, through that powerful GitOps reconciliation loop. At first glance, this certainly looks like three distinct tiers. Tier 1 is the SMO, Tier 2 is the Nephio management cluster, and Tier 3 is the final OCloud workload cluster. So, how on earth do we resolve this apparent conflict? The resolution, the elegant and absolutely crucial component that makes everything work together seamlessly, is what the source material refers to as a shim layer or an adapter. This piece of software is the unsung hero of this entire architectural story. Its entire purpose in life is to be a translator, an intermediary that sits right between the world of the ORAN standard and the world of the Nephio native implementation. It is designed specifically to bridge that gap, to absorb the differences between the two models, and ultimately to make the three-tier implementation behave and appear exactly as the two-tier standard expects it to. It is a classic and truly beautiful example of a software engineering adapter pattern in action.
So let's get very specific about how this brilliant little shim layer actually works. It has two faces. It has a northbound face that looks up towards the SMO, and it has a southbound face that looks down towards Nephio. Looking northbound, this shim layer exposes a perfectly standard, compliant, by-the-book ORAN O2 IMS API. As far as the SMO's FOCOM function is concerned, it believes it is talking directly to a standard OCloud. It makes a standard REST API call to request a new cluster, exactly as the ORAN specification says it should. It is completely unaware of the complex, powerful machinery that sits behind that API endpoint. But then, looking southbound, the shim layer performs its translation magic. It takes that standard O2 API call that it just received, and it transforms the information within it into the Nephio-specific, high-level intent custom resource, that simple YAML declaration that we saw way back in step 1 of our workflow. It then submits that native Nephio intent CR to the Nephio management cluster, which in turn kicks off the entire curation, specialization, and GitOps reconciliation process we detailed so carefully. The result is truly elegant. The SMO is happy because it's speaking its native language to a fully standard interface. Nephio is happy because it's receiving the high-level declarative intent it is designed to process. The shim layer acts as a universal adapter, making the logically three-tiered Nephio system appear to the outside world as a fully compliant two-tiered system. It perfectly and cleanly reconciles the standard with this powerful modern implementation.
To conclude our truly deep dive, let's now zoom back out from the microscopic details to the macroscopic vision. We have spent a great deal of time on the meticulous, step-by-step mechanics of how Nephio implements just one interface, the O2 IMS interface, for automating cloud infrastructure. But the true power, the true elegance, and the ultimate promise of the Nephio model is that this is not a one-off, bespoke solution for a single problem. As we will see in this final section, the core principles we have just learned and internalized, intent-driven, declarative, curation, and GitHub space reconciliation, are a universal pattern. They are a grand unified theory that can be applied across the entire network automation landscape.
This slide reveals the incredible consistency and the breadth of the Nephio vision. The complex, powerful workflow that we spent so much time dissecting for O2 IMS is not unique, it's a reusable pattern. For O2 DMS, which is responsible for deploying workloads onto the infrastructure we just built, the process is philosophically identical. The SMO would state a high-level intent like, deploy a high-performance 5G CU network function on cluster X. Nephio would then use a base package for that CU, curate it with specific parameters like network attachments and capacity, push the final configuration to a Git repo, and a reconciler running on the target cluster would then deploy the CU pods. It is the exact same pattern. And it extends even further. As our source material mentions, this same model can also be applied to the O1 interface, which handles the ongoing day-end configuration of the running network functions, often using a protocol like netconf. An operator could express a high-level intent like, increase the cell capacity in this sector by 20%. A specialized Nephio controller could translate that business intent into the dozens of specific, low-level netconf commands required, and then use a reconciliation loop to ensure the live network function's configuration always matches that desired state. The sheer beauty of this model is its unified, consistent approach to every single aspect of network automation.
This table perfectly summarizes the entire Nephio philosophy in a single, powerful view. It doesn't matter what management task you're performing, whether it's provisioning infrastructure, deploying workloads, or managing ongoing configuration, the approach remains consistent. You always start with a high-level intent, which is expressed as pure data. That intent is then translated through that process of curation into a specific declarative artifact, which in the Kubernetes world is a custom resource or a CR. And that CR is then actioned by a specialized controller that performs a continuous, closed-loop reconciliation to make reality match the declared state. This elegant pattern of intent, CR, reconciliation is the single unifying theme. It's the core engine that drives automation across the O2 IMS interface, the O2 DMS interface, and the O1 interface. It provides a single, consistent, predictable, and powerful way to manage the entire complex lifecycle of a modern network.
And so, this brings us to the end of our journey, and to our final thought. We have traveled from the rigid, monolithic past of telecommunications all the way to the open and disaggregated present. We have deconstructed the complex ORAN architecture, and we have seen in intimate detail how a powerful, declarative engine like Nephio can bring that architecture to autonomous life. This model, where we, as operators, simply declare our desired outcome, and intelligent, autonomous systems work tirelessly and relentlessly to make it so, represents a change in network operations as profound as the invention of the assembly line was to manufacturing. It promises to dramatically reduce human error, increase the speed and agility of service delivery to unprecedented levels, and manage a scale of complexity that is simply beyond human cognitive ability. Which leads us to the final, provocative question that this technology forces us to ask. With tools and philosophies like these, are we finally, truly, entering the era of the self-driving network? Thank you for joining this deep dive explainer.